Now I am going to discuss about a linear transformer. The transformers work on the principle of mutual inductance. Okay, that is what we have discussed in the previous lectures, and we have solved few problems on mutual inductance also to understand the concept of mutual inductance. So if I consider the linear transformer, it will be having primary circuit and a secondary circuit. The primary circuit will be having source and secondary circuit will be having load, and in primary and secondary winding we will be having resistances. Okay, resistance also to be considered. Okay, that is why the circuit is drawn like this. Okay, along with the coil we have some resistances, R1 in the primary side and R2 in the secondary side. Okay, so in the first mesh we have source, and we call that as primary, and in the second mesh we have load, so we call it as secondary, and we will assume that the transformer is linear. Okay, we are going to assume that the transformer is linear, and two resistors serve to account for the resistance of the wire out of which the primary and secondary coils are wound. Okay, so each and every, for example, in the primary side we have a resistance R1, and the secondary side we have a resistance of R2. Okay, here if I have a circuit like this, there is a possibility of reflected impedance. So some part of the impedance will be reflected from the secondary side to the primary side. That is what we are going to calculate now. Okay, just consider the circuit which is available. Okay, for the linear circuit, we are going to apply KVL for both the meshes. Okay, first I am going to apply KVL for the mesh 1. Okay, so we can start with minus V1 plus R1 I1. Okay, this is minus, not minus V1, minus Vs. Okay, the source voltage is considered as Vs here. Okay, source voltage is considered as Vs. So minus Vs plus R1 times I1. Okay, R1 times I1, and there is a self-induced voltage across this. So L1 will be written as J omega L1. Okay, L1 can be written as J omega L1, and M can be written as J omega M. M can be written as J omega M. L2 can be written as J omega L2. L2 can be written as J omega L2 in the frequency domain or phasor domain. So it is important that we need to convert this circuit into frequency domain if I need to apply KVL. Okay, so it will be easy for us to solve. So that is why we are considering that in the phasor domain. So we have minus Vs plus R1 I1. For resistance there is no issues. Okay, in the case of inductance we have two types of voltage across it. One is self-induced voltage, that will be J omega L1 times I1. Okay, this J omega L1 times I1 is a self-induced voltage, and there is another voltage due to the current I2 flowing through L2. Here I2 is entering the undotted terminal, so generator voltage positive across the L1 will be at undotted, negative will be at the dotted terminal, and generator voltage will be J omega M multiplied by I2, because it was due to the current I2 this voltage is generated. Okay, now check the direction of current I1. I1 is entering negative and leaving positive, so it does not obey the passive sign convention, so I will put minus sign here. Okay, J omega M I2. Okay, J omega M I2 equal to 0. So I am going to rearrange it to get Vs equal to R1 I1 plus J omega L1 I1, and this J omega I2, which is equation number 1. Okay. So now so next I need to apply KVL in the mesh 2. I am applying KVL in the mesh 2. If I am applying KVL in the mesh 2, I can write R2 I2. So R2 I2 can be written as it is. Okay, and then ZL I2. Okay, we don't know the impedance value, we are considering the impedance as Z. So ZL I2. Okay, So R2 I2 can be taken as it is, ZL I2 can be taken as it is. Across this we'll be having two voltages. One is due to self-induced voltage. So L2 will be written like j omega L2. Okay, so j omega L2 I2. Okay, j omega L2 I2. So we have R2 I2, ZL I2, j omega L2 I2, which is self-induced voltage, and there will be a mutually induced voltage due to the current I1. Here the current I1 is entering the dot. So generated voltage across the L2, positive will be at the dot, negative will be at the undotted. Okay, the voltage can be written by using this. M can be written as j omega M. So we can write j omega M. Okay, it was due to the current I1, so multiplied by I1. Okay, now check the direction of current I2. I2 is entering negative and leaving positive. So it does not obey passive sign convention. So we'll get minus j omega M I1. So we got minus j omega M I1. Okay, I'm going to rearrange it and I'm going to write I2 in terms of I1. So if I write I2 in terms of I1, I'll be getting something like this. I2 equal to j omega M I1 by R2 plus j omega L2 plus ZL. Now substitute this I2 in equation number 1. Okay, this is my equation number 1. Okay, substitute I2 in equation number 1. Okay, so I'll be getting the equation of for Vs with respect to I1. With respect to I1. Okay, so I'm just substituting I2 equal to j omega M I1 by R2 plus omega L2 plus Z. Okay, this I2 is substituted. If I substitute and perform the calculation, I will be getting the equation like this. Z equal to, okay, actually Vs is equal to R1 plus j omega L1 plus omega square M square by R2 plus j omega L2 plus ZL times I1. It is just a mathematical calculation. Please do it on your own. Okay, so here I am going to take this I1 to the left hand side. So Vs by I1 will be equal to R1 plus j omega L1, okay, plus omega square M square by R2 plus j omega L2 plus ZL. So this is what I'll get. So in that case, this part is the reflected impedance. Okay, this is due to the primary side. L1 is at primary side and R1 is also at primary side. So impedance caused by this is from the primary side, but this involves the secondary side. We have load which is reflecting here, R2 is reflecting here, okay, L2 is reflecting here. Okay, so this we call it as reflected impedance. Okay, so I am going to represent that as ZR. Okay, this is written separately here. ZR. It is also called as coupled impedance. It is also called as coupled impedance. Okay, you can expect some 8 or 7 marks question. Okay, as a theory question for the linear transformer. Okay, thank you.